Hello, today we're going to present some exploration of Nalu, the CFD code from Sandia on AWS, ARM, and x86 systems. And this work is collaborative work with myself, Srinath Vadlamani from ARM, and Steve Messenger at AWS.
The motivation for this effort is to help answer how well do scientific production codes run on ARM-based systems. This work helps to answer the question with a major production code from the US National Labs. Not only is Nalu a mission-critical code for NNSA, it shares many framework components with other more sensitive codes at Sandia's, such as the export-controlled Spark CFD code. So, by understanding Nalu's performance on E2C at Amazon, we gain some insight as to how other mission-critical codes may perform on such a system. This talk will begin with an explanation for how we made our comparisons, in the spirit of fairness. We will then give a brief overview of the Nalu code itself and the case we have chosen for this study. We will then present some performance results on the AWS EC2 parallel clusters, which will be followed by concluding remarks. It is important that when we are comparing platforms for simulation efficacy, we do it both fairly and with some hopes of reproducibility. Fairness can be considered as use the best software stack for the mic architecture, such as on Intel, only use Intel compilers. We choose fairness as use the most similar software stack across platforms. There are merits to both. In choosing GCC 11.1 as our compiler across platforms, we are assured some level of consistency. Also, this study may spur members of the open source GCC effort to look at some of our exposed deficiencies. The SPAC package manager has been chosen to help with a fair comparison, all the while allowing for reproducibility. Our hope is that if one gets on a Graviton 2 or Skylake at EC2 and follow the directions at the bottom of the slide, they will be able to reproduce the results presented in this talk. Please feel free to contact myself if help is needed with such a corroborative effort. Nalu was chosen because it is 1. Used for computational scientific efforts currently. 2. The software stack uses many of the cutting-edge numerical packages actively being developed at the US labs for HPC simulations, which they themselves are complicated and tend to stress performance on modern computing systems. 3. Nalu has been used as acceptance criteria for HPC systems in the past. So what is Nalu? Sandia stewards this low Mach number computational fluid dynamics code, which uses a framework known as the SIERRA framework. This framework is a collection of many packages that are made available via modules across many HPC systems at the National Labs. Trilinos and Cocos are noted members of the SIERRA framework. Nalu itself has been used in cases such as simulating jet flows that have combustion attributes. We have chosen a case that has a large number of finite elements so that we have a reasonable computational load per core. It is a simulation of a jet flow, and we run it for 25 time steps. It is known that the momentum solve of the system is the most expensive part of the computation. In this case, we are using Trilinos' new linear solver efforts as opposed to SuperLU used in past comparative efforts. Slide 6 is a quick comparative table of the silicon in this effort. The experiment is using the N offerings from EC2, which is the Skylake and Graviton 2 nodes using Amazon's Elastic Fabric Adapter, EFA, with a 100 gigabit per second network. We run the experiments with full node usage. After we did a low node count exploration, it was determined that one thread per core and n MPI ranks equal to the number of cores per node was the best configuration for performance. This full MPI node saturation configuration is used throughout the experiment. This first chart shows results that both systems scale well, up to 64 nodes, while the C6GN Graviton 2 system outperforms the x86 C5Ns. The vertical axis shows speedup versus 2 C5N node solution time, which is the smallest node count that can handle this experiment case. Even larger cases, i.e. more resolved meshes using more finite elements, are available, which would allow for scaling out to a larger number of nodes. So, if it is desired to stress test all the racks that AWS has to offer in a warehouse, that is possible with the Nalu available experiments of a JetFlow. Slide 8's chart is a little busy while trying to convey that the Graviton 2 system is comparatively cost effective. Also note that it costs about the same to get to the solution, in this case 25 iterations, up to 64 nodes, which establishes a type of parallel computing of efficacy. On the C6GNs, it costs about the same to get to the solution in less than 1/30th of the time as on 2 nodes of the C5N. At 16 nodes, we see the C6GN is almost 3.5 times more cost effective than its Intel counterpart. Do note that on-demand pricing was used to make these quantitative comparisons. Since we have some scaling behavior for this test case, it is a wonder as to how well we are using a node onto itself. We see a forge map profile view of 64 nodes running on the C5Ns. At first glance, we see very poor usage of vector instructions. An obj dump exploration for the ZMM AVX512 vector registers was null. So, even though SPAC was using -mtune equals skylake -avx512 as the default microarchitecture detected flag, the compiler may not be issuing good vector code for Cocos, particularly the Bellows and the mu-lu iterative solver packages. Slide 10 is a profile on the aarch64 C6GNs for the same node count of 64. The hotspot also resides in the Bellows linear solver framework. Even though we recently instantiated nodes with perf event paranoid with value of -1, the profiler is not reporting floating point events. Hopefully, this effort is going to nudge a revisit of such profiling on Graviton 2 chips. It seems that perf doesn't show floating point events for an Amazon Linux 2 instantiation of the Graviton 2s. But we do conjecture that when vector use is increased, We should see scaling out to more nodes and better solution times overall on both systems. We hope this piques the interest of the COCOS team for some collaborative work. In conclusion, we have demonstrated the efficacy of C6G versus C5 with a real production code, with a real simulation case, both in parallel efficiency and cost. Our experiment management choice of using SPAC allows for productivity after some SPAC edits available from the declared fork, and portability, which is across all platforms, with reproducibility. Do note that using SPAC with both the Intel and ARM compilers with the Nalu package is going to need some work. This effort hopefully piques COCOS and SPAC developers to start collaborative efforts, using this as a baseline study to increase efficiency on the EC2 systems, especially with vector usage. We thank you for your time and leave you with some references.